In this video I'm going to consider vanadium 2p. Previously I used regions to construct a peak model that just targeted the vanadium 2p, but now I will use only one region and a set of components that will allow the construction of a background over this interval that ought to be very similar to the one that I ultimately used to fit these data, where I excluded the oxygen 1s using a region with a background type of null. So the first thing that I would like to do is obtain an approximation to the vanadium 2p that is measured from metallic vanadium. So this is a vanadium foil that has been sputtered to remove all the oxygen. There's no oxygen signal here that we can perceive, and I've constructed a background which is just a Shirley background, and the Shirley background spans the entire interval. This is the first region defined on the regions property page, and then I've used two subsequent regions where I've picked out intervals that approximate where the vanadium 1/2 and the vanadium 1/2 peaks from vanadium 2p are located, and when I calculate using the relative sensitivity factors that are appropriate for these two separated doublet signals, I should get the same amount of vanadium. So my test is, when I correct for the relative sensitivity for these two photoemission lines, I ought to get the same 50-50 in terms of the amount of vanadium, and that's what you'd expect if I wanted to do quantification using either one of these. If I wanted to use both peaks, so for example the region that represents where the Shirley background goes, then I would use the total RSF, and when I use the total RSF, because the total RSF is now integrating over this entire interval, I end up with 3 different RSFs, but they all produce the same answer in terms of the amount of vanadium, and that's exactly what we would like out of relative sensitivity factors and targeted regions that are appropriate for these sensitivity factors. The next step, having validated these data as being suitable for representing vanadium 2 metallic signal, is to construct a line shape that I can then add to other peak models. In order to construct a line shape, I need to subtract from the photoemission signal the background, and this can be achieved using an option on the test data property page of the spectrum processing dialog window. This is the background subtract, and when I press this button, the data are processed to remove the Shirley background. So now we see genuinely processed data. This is not a display option. The BG subtract button on the toolbar that I'm indicating, this will only change the display mode. However, there is a processing statement that indicates now on these data that processing has been performed to remove the background, and it's selected in the right hand side. So if I want to copy the data in the process form to my file in which I would like to construct a peak model, I can use the toolbar button that says copy paste VAMAS blocks, or there's this new toolbar button that will copy the VAMAS block to a new column in a new file. And this has the advantage that it automatically ticks the process data only, and it indicates the file and the VAMAS block that will be copied. The process data will come through, and it should provide us with the data in a form suitable for constructing a line shape from data for a component in a peak model. The last thing I need to do is make an adjustment to the name of the VAMAS block, the block ID, and to make use of these data as a line shape I need a prefix and then a name, and that must be a unique name. So no other VAMAS block should have this name, and that is the case. So if I change the VAMAS block to the new VAMAS block ID. It then appears in the quantification parameters dialog window, the top field. So I can copy that and use that as the line shape name in any peak model that I now construct. So let's do that construction of a peak model, and it will involve a background. We must have a background. There's always an offset in intensity that must be accommodated if we're going to construct a peak model. So I'm going to use, in this case, rather than a Shirley background, a min limits background type. And what that does is it provides me with a constant background that is determined from the minimum of the two limits of the background. So if I were to choose the interval over here, you can see how the minimum limits is always on the right hand side. It could be on the left hand side depending on my choice. For example, here I've chosen a min limits where the minimum is now on the left hand side, not the right hand side. But in terms of these data, I'm going to select only the vanadium 2p interval, not including the oxygen 1s. And previously I made use of regions to remove the oxygen 1s from my peak model, but in this case I'm simply going to construct a peak model for the vanadium 2p. So let's add some components, and these components we need to enforce the 1:2 ratio. That will be important when we try to fit these data. There must be other solutions. If we just put two components without any constraints, that would fit data but without any physical meaning. So this is the first step in trying to produce the physical meaning that we know must be there because of the doublet characteristics of vanadium 2p. So let us next copy these two components and construct components that represent background signal. And these are effectively Shirley backgrounds that are calculated directly from the line shapes. And I just want to introduce some additional constraints, such as I would like each one of these backgrounds to position themselves beneath the two component peaks. I would also like the backgrounds to have the same full width half maximum parameter as the two component peaks. So these are relational constraints that are between these bell-shaped curves and S-shaped curves that ultimately will fit these data. The limit of the background will be defined by this region. It's a flat background, and on top of that I ought to get two components that represent a Shirley lift and two components that represent the photoemission of vanadium 2p. The next step is then to attempt a fit, and we see now the Shirley type shapes that are generated from these components and the components in the ratio of 2:1. Let me just set the background to have 0 RSF so they do not contribute to any calculations of the amount of substance, the concentration. So it's in the 2:1 ratio that we require. Now the final step is to try and model the metallic signal. I'm going to do that by using the name that I've created for the line shape for the metallic signal, and I need to create a component which I can then assign that line shape to, and even by I can see that I've got adjustments that will be made to the peak model when I say fit. Let's use a chi-square, and here it is. We've now got a peak model that represents two components representing the oxide, one component which is actually a doublet, a full doublet, which represents the metal, and then we have background. That represents no signal that we would like to include in a quantification. And here we see, by virtue of the component indices, the various components that contribute to this peak model, and they've been fitted to the data without reference to the oxygen 1s, and it has produced a background shape that is very similar to the background that was constructed over the entire region that included the oxygen. So this is a method for trying to reproduce a Shirley background over a limited interval where we perhaps don't have all the data that would be necessary to fit the peak model to the data. Now you may have observed that I have not yet introduced a background component that corresponds to the metallic peak. And this ought to have some bearing on this peak model, and that's because we consider this metal to be a layer beneath the oxide, and as a buried layer you would expect a response in the background that is disproportionate to the amount of signal that we see. Whenever we have attenuation to inelastic scattering of a photoemission peak, that attenuation appears within the background. So we should not underestimate the amount of background signal that will be generated by the metal. And we can try and approximate this if we take the component that represents the metal and paste that component into the peak model, adding, let's put in the prefix that turns this into a Shirley background, and let's try and add to the intensity of that background as if it is more than you might expect. I'll set that to a different component index for the background. I'll set it to a positive value this time. Negative value, -1, means that you can display photoemission peaks with positive values, non-negative values rather, as photoemission peaks on top of background components that have the -1 as the component index. So I'm going to set this to 4 so we can see this as a different color, and you can see that I've overestimated by adding more intensity to the background signal than perhaps is warranted. And then if I say fit, I start to see an adjustment to the peak model. It's an adjustment to the background, in fact, predominantly, that is perhaps again not entirely warranted, because I do not wish this to alter in position relative to the photoemission peak, which it has done. So the background component is not sitting beneath the metal peak, and that may have influenced how well the data has been adjusted in that optimization step. And yes, there was a difference. Once I forced the component that represents the background for the metal to sit beneath the metal peak, then we get a different answer. And we get a reasonable answer in terms of a residual and the residual standard deviation. So here we can see a peak model which, if I return the value to -1, produces the type of shape that we saw previously in the first video for vanadium, where I used regions where one region represented a Shirley background from the right hand side all the way to the left hand side of the oxygen 1s, and that calculated Shirley background was very similar in shape to what we see here. And I've reconstructed this using components that represent the background, and I've enforced the relationship between the vanadium 3/2 peak, the vanadium 2p 3/2 peak, and the vanadium 2p 1/2 peak, 2:1 ratio. So these are all important to getting a fit to the data that we see here.